So today we will start with the first topic of this course, atomic structure and mole concept. The topics will be covered in this chapter are Planck's quantum theory, Bohr's theory, and then atomic spectra, Sommerfeld theory, uncertainty principle, Pauli's exclusion principle, wave mechanics, Schrödinger equation, and lastly we will cover concept of molarity, molality and mole fraction. So, how the atomic model was developed? So, Dalton's model first came. So, it says that atoms are indivisible particles, atoms of same element are identical, different atoms combine to form compounds. Then came Thomson's model. So, Thomson discovers the electron plumb pudding model, in which negatively charged electrons embedded in a positive sphere. Then Rutherford model was introduced by Rutherford carried out one gold foil experiment, and he discovered the nucleus atom, and he said that atom mostly has empty spaces, electrons orbit around a central positive nucleus. Now, what are the failures of classical mechanics? Electrons as charged particles should continually emit energy as they orbit the nucleus via electromagnetic radiation, eventually spiraling into the nucleus, while it is observed that atoms are stable and electrons do not collapse. We will discuss this thing elaborately later. Classical theory is not able to explain the discrete line spectra. Classical mechanics could not explain certain phenomena like photoelectric effect and blackbody radiation. So, first we will start with Planck's quantum theory. So, a brief introduction here is in 1900 Max Planck explained the particle nature of light with his theory known as Planck's quantum theory. Planck proposed that light consists of discrete packets of energy called quantum. It solved the mysteries of blackbody emissions in the ultraviolet region. The equations of Maxwell in classical mechanics and the study of electromagnetic radiations by Hertz successfully proved the wave character of light with the phenomena such as diffraction and interference. Planck's quantum theory proposed the quantum nature of electromagnetic radiant energies. It explained the interaction of light as a particle with the matter. It proves the particle character of light with the phenomena such as the photoelectric effect and blackbody radiations. It is the basic theory of quantum mechanics, and it paved the way for the dual character of matter. So, what are the postulates of Planck's quantum theory? These are the main postulates of Planck quantum theory. First postulate is a body can absorb and emit discontinuously tiny packets of energy. Each small energy packet is known as quantum. Uniquely, the term photon denotes light energy. Energy associated with quantum varies directly with the frequency of electromagnetic radiation. So, E is h nu for single photon, and when n number of photons are used, so expression is E is n h nu, where n is a whole number or integer, positive integer, where E is the energy of the quantum and h is Planck's constant we know, and nu is the frequency of electromagnetic radiation, and n is a non-zero positive integer as I mentioned before. So, as I mentioned before, according to Planck's theory, the energies are quantized. So, you can see these are the quantized, not like continuous here, it is like a ramp versus stairs. So, you get h is E by nu, where h is Planck's constant and E is energy of light and nu is frequency of photon. When Planck researched blackbody emissions in 1900, he found that a proportionality constant is essential in his empirical formula to match the experimental result, because E is proportional to the frequency nu. So a proportionality constant is required. With effort, he calculated the value of Planck's constant to measure the quantum energy. So, what is the value of Planck constant? We all know the value of Planck constant is 6.626 times 10 to the raise minus 34 joules second in the SI unit. And if you consider CGS system, which is nowadays nobody is using, the value of Planck's constant is 6.626 times 10 to the minus 27 arc per second. So, in the atomic unit, H value is 4.3136 times 10 to the raise minus 15 electron volt second. Okay. So, you can convert different values of Planck constant. Suppose you start with SI unit and 1 joule is 10 to the 7 arc. So, you get in the CGS unit value of a Planck constant in CGS unit, or you can use this conversion factor. 1 electron volt is 1.602 times 10 to the minus 19 joule. So, you can actually convert the Planck's constant from joule per second to electron volt per second. So, as we all know, E is h nu. Okay. So, if we so low frequency radiations contain low energy, conversely high energetic radiations possess high frequencies. So, what is the relationship between the energy and then lambda or wavelength? So, we know that okay. So, E is if we substitute nu the frequency by c by lambda, c is the velocity of light and lambda is the wavelength of the light radiation. So, you can actually convert E is h nu to E is h nu by lambda. Here lambda is the wavelength of the light radiation. So, as I mentioned, so E is the magnitude of energy of photon, h is Planck's constant and its value is 6.626 times 10 to the minus 34 joule second, and c is the velocity of light in vacuum and its value is 3 times 10 to the 8 meter per second in the SI system, and lambda is the wavelength of light. Now, by substituting the value of Planck constant, the velocity of light in the above equation, we get E is 6.626 if we put the value of h here, and if we put the value of c here, we get E is 19.878 times 10 to the minus 26 joules by lambda. So, with this equation, we can calculate the energy of light radiation from its wavelength data. So, what is the overview of Planck's quantum theory? So, Planck's quantum theory explains the quantum mechanical phenomena of thermal electromagnetic radiations emitted by black bodies. It determines the spectral density of black body radiations at a constant temperature when there is no net flow of matter or energy between the black body and its surrounding. Planck discovered the term quantum or to denote the minimum amount of energy emitted or absorbed by the oscillator. The amount of energy less than a quantum is neither emitted nor absorbed. So, if the value of energy is less than one quantum, then there will not be any emission or absorption of light. The incremental energy changes of the black body emissions showed their spectral intensity from low frequency to higher frequency radiations. Hence, at thermal equilibrium, the radiation released from the cavity of the black body experimentally agreed with the quantum assumptions of Max Planck. Next, we will talk about applications of Planck's quantum theory. So, Planck's quantum theory is the fundamental theory of quantum mechanics. It has the following applications. The semiconductor based electronic gadgets follow the quantum nature of matter. Fiber optic telecommunication and laser devices involve the phenomena of photon interaction with matter. Atomic clocks fitted in satellites for GPS navigation follow quantum physics, and MRI or magnetic resonance imaging we observe in different hospitals. Scan works on the quantum nature of the light and matter. Then what are the limitations of Planck's quantum theory? There are some limitations also. So, here we will discuss the limitations of Planck's quantum theory. It has limited scope. It could only be applied to explain black body radiation and was not a complete theory for other phenomena such as the spectra of helium or more complex atoms. Another limitation of Planck's quantum theory is it is an incomplete mathematical framework. It did not provide a full fundamental formalism or a physical explanation for its quantization rules, which were introduced as an ad hoc assumption. So, it was the assumption that energies are quantized, but there was no formalism, mathematical formalism there. Then spectral lines issue. The theory could not explain the intensities of spectral lines or account for phenomena like the anomalous Zeeman effect, which is related to electron spin. It also lacks of wave particle duality. It treated radiation as discrete packets of energy or photons, but did not incorporate its wave-like properties. There are some missing key concepts, like it did not address other fundamental quantum concepts like electron spin, the Pauli exclusion principle, or the wave particle duality of matter. No explanation for dispersion. It failed to provide an explanation for the dispersion of light. No link to other physics. It did not connect with other areas of physics such as the concept of gravity. So Planck's quantum theory does not discuss about the gravity. Then came Bohr's atomic model that most of us we already studied. So Bohr's atomic model and the atomic spectra. So what are the postulates of Bohr's atomic theory? First postulate is the electron in an atom has only certain definite stationary states of motion allowed to it. Each of these stationary states has a definite fixed energy. Each orbit corresponds to a specific energy level and is characterized by a principal quantum number n, where n varies from 1, 2, 3, etc. The angular momentum of an electron in an orbit is quantized and is given by mvr times nh by 2 pi. So here nh by 2 pi are missing. So here nh by 2 pi are missing. Okay. So where m is the electron mass, v is the velocity, and r is the radius, where n equals to 1 to 3 and h is Planck's constant. Electrons can jump between orbits by absorbing or emitting energy equals to the difference in their energy level. So delta E is your h nu, means E final minus E initial, where nu is the frequency of radiation emitted or absorbed. So next we discuss Bohr's atomic model and the atomic spectra. First start with postulates of Bohr's atomic theory. It says that the electron in an atom has only certain definite stationary states of motion allowed to it. Each of these stationary states has a definite fixed energy. Each orbit corresponds to a specific energy level and is characterized by a principal quantum number n, and where n varies from 1, 2, 3, etc. The angular momentum of an electron in an orbit is quantized and is given by mvr is nh by 2 pi, where h is Planck's constant and n is principal quantum number, and v is the velocity, r is the radius of the orbit, and m is the mass of the electron. Electrons can jump between orbits by absorbing or emitting energy equal to the difference in their energy levels. So if the difference in the energy levels is delta E, which is denoted by E final, energy of the final state, minus energy of the initial state. So we can write delta E, which is equal to h nu. So we can write h nu equals to Ef minus Ei, where mu is the frequency of radiation emitted or absorbed. So electrons can move in different orbits. So this is n equals to 1, this is n equals to 2, and n equals to 3, and this is the nucleus. And here you can see in this video, so this is the nucleus, and the electrons, they are actually moving in different orbits. Now for a stable system, the force of attraction between the nucleus and the electron is equal to the centrifugal force of the moving electron. So if there is no rotation of the electrons, then those electrons, it will fall on the nucleus, and the atom will be unstable. So this Coulombic force has to be balanced by this centrifugal force. So we can write Coulombic force equals to centrifugal force, and we can write mv square by r, where m and v are the mass and velocity of the electron, and if z is the number of units of element charge E on the atomic nucleus, or number of protons, and r is the electron nucleus separation. So we can write actually, so Coulombic force we know k times k is one constant, z is square by r square equals to mv square by r square. So basically we can write it like Coulombic force is k z is square by r square is mv square by r, and if we cancel r in the denominator, So, we can basically arrive at this expression kz square by r is mv square. So, k, the value of k is 1 pi 4 epsilon naught. So, according to Bohr's postulate for the angular momentum, mvr is nh by 2 pi, again n is the quantum number where h is Planck constant, and eliminating nu between equation, if we eliminate in equation 1 and 2, so we get r. So, the value of r from equation 1 and 2 we get n square h square by 2 pi square m k z square. So, it appears that only certain orbits whose radii matches equation 3 are allowed for the electrons. Now, let us consider the total energy E of the electron, which is the sum of kinetic energy. Kinetic energy we can express by half mv square, and the potential energy is minus k z square by r. So, we get total E is half mv square minus k, sign will be minus here because there is attraction between the nucleus and the electron. So, attractive force here, so that is why you get the minus sign. So, minus k z square by r. So, we can write then, we can simplify. So, we get E is minus half k z square by r. So, if we substitute the value of r here from equation 3 here, we get the equation or the expression for energy E is minus 2 pi square k m z square e to the 4 by n square times h square. So, according to Bohr's second postulate, the energy of any photon radiated by the atom should be equal to the difference in the energy of the two levels. So, delta E we have already seen, delta E is h nu. So, if we substitute the value here, suppose EF is your NF and EI is NI, if we substitute this, we arrive at this expression. H nu is 2 pi square k m z square e to the 4 by h square y 1 by n square minus n f square minus 1 by ni square. Okay, so basically what you get here is, so this is actually the correct expression is 1 by nf square minus 1 by ni square. Okay, so this is the correct expression. Yeah, here you can see the value of nu is 2 pi square k m z square e to the 4 by h to the 3 now 1 by nf square minus 1 by ni square. Now, if nf is equal to 2, then the constant term evaluated, this expression is in the numerical agreement with the formula which Balmer had found from the experimental hydrogen atom spectrum. In other words, the Bohr's expression was in agreement with the known experimental spectrum of hydrogen atom. So, from there we can actually calculate the radius of Bohr's orbit. So, according to Bohr, the radius of orbit in which electron moves is shown here. So, Rn is n square h square by 2 pi whole square and then mz square k. So, where k is Coulombic constant and the value of is 9 times 10 to the 9 Newton meter squares, Coulomb to the minus 2. So, if you substitute every value here, so we get value of Rn is 0.529 n square by z square angstrom. We can also calculate the velocity of electron in different orbital. So, from the quantization of angular momentum, we get mvr is nh by 2 pi, I already discussed. Here we consider me is the mass of one electron, and v is the velocity of electron in nth orbital. So, vn, if we substitute here, we get nh by 2 pi me rn, where if you now put the value of r, if we put the value of Rn, we arrive at this expression. So, we can see the radius or the radius of Bohr's orbit, it depends on n square by z square, okay, directly proportional with n and inversely proportional with the z. And here the velocity of an electron in an orbit is inversely proportional to the n, value of n or quantum number, principal quantum number, and is directly proportional to the z or atomic number. Then we can also calculate the energy of electron in Bohr's orbit. the total energy of electron is E is minus k z d square by r. So, if we substitute again the value of r here, so we get this expression twice pi square m z square e to the 4 k square by n square times h square. Now, if we substitute the value of m, means mass of an electron, k, h and pi, we get minus 13.6 z square by n square electron volt. So, you can see that okay, it is directly proportional, E is directly proportional to z square and E is inversely proportional to 1 by n square. When an electron jumps from an outer orbit or higher energy n2 to an inner orbit or lower energy n1, then the energy emitted in the form of radiation is given by, so delta E is your En2 minus En1. So, if we substitute 13.6 z square, then we get 1 by n2 square minus 1 by n1 square, okay, 1 by n1 square minus 1 by n2 square electron volt. So, we know E is h nu and C is C nu is C by lambda, and nu bar wave number is 1 by lambda or 1 by wavelength. So, we get wave number is delta E by hc. So, if we substitute everything, we arrived at this expression nu bar. And this constant term, if you see twice pi square k square e to the 4 z square by Chq, this is called Rydberg constant or Rh. Okay, so Rydberg constant usually we write as Rh, and its value is 109678 centimeter inverse. Now, since here the energies are quantized, so we can actually explain the hydrogen atom spectra on the basis of Bohr atomic model. The light absorbed or emitted as a result of an electron changing orbits produces characteristic absorption or emission spectra, which can be recorded on the photographic plates as a series of lines. The optical spectrum of hydrogen consists of several series of lines called Lyman, Balmer, Paschen, Brackett, Pfund and Humphrey. These spectral series were named by the name of scientists who discovered them. So, you can see, so for Lyman series, the value of NF is 1 and Ni can be 2, 3, 4, 5, 6, etc. Similarly, for Balmer series, the NF or the final quantum number is 2 and the value of Ni can be 3, 4, 5, 6, 7, 8, etc. And for Paschen series, it is n equals to 3 is the value of NF, and Ni again 4, 5, 6, etc. and so on. Now, what we can see here, as we move from n1 n equals to 1 to n equals to 2, and then from n equals to 2 to n equals to 3 and so on, we can see the gap or energy gap between two consecutive energy level decreases. If that is so, okay, so that is why we are for Lyman series, since the value of NF or the final quantum number n so is 1, so the light we get, it falls in the UV range. For Balmer series, it falls in the visible range. For Paschen, Brackett, Pfund and Humphrey series, it falls in IR range and so on. Now, what are the advantages of Bohr's atomic theory? It explains the line spectra as we just seen. It explains the stability of atoms. From there, we can calculate the energy of different orbitals and radius of first orbit of hydrogen and hydrogen-like atoms. It gives us an idea of principal quantum number. It also gives us an idea of quantized energy levels, that is E is proportional to nu. Now, there are some limitations of Bohr's atomic model, such like it could not explain the line spectra multi-electronic system. So, for hydrogen-like system, like for hydrogen or Li plus and so on, we can apply Bohr atomic theory, but for other line spectra, for multi-electronic system, we cannot use Bohr's atomic theory. It is unable to explain the Zeeman effect and Stark effect, which tells us about the fine structure of atoms. Bohr's model explains the two-dimensional model of atom, but not the actual three-dimensional model of atom. It could not explain the dual nature of particle and Heisenberg's uncertainty principle. So, these are the limitations of Bohr's atomic model. So, how this slide shows how evolution of atomic model takes place. So, initially in 1803, Dalton considered solid sphere model here. Then Thomson, as I mentioned, okay, he considered plum pudding model like this. And then in 1911, Rutherford considered like this is the nucleus and electrons are in different it surrounds the nucleus and it forms like a cloud here. And Bohr model, it says that okay, so you have the nucleus here and electrons are moving in different orbits, circular paths. And then quantum models come in 1926 by Schrödinger. We will discuss it later. So, after Bohr's model, we will discuss Sommerfeld's model. In 1915, Sommerfeld extended Bohr's atomic model. He proposed that instead of electrons moving in only circular orbits, they revolved around the nucleus in elliptical orbit like this, you can see here. According to Sommerfeld, the nuclear charge affects the electron's motion in an atom. The electron does not revolve in a singular circular path, but adjusts its rotation in multiple elliptical orbits. These elliptical orbits have varying eccentricities. The nucleus is fixed at one of the foci of the elliptical orbit. You can see it here. So, in Sommerfeld's model, the position of an electron in an elliptical orbit is determined by two varying parameters, the distance from the nucleus r and the angular position phi. Thus, permitted elliptical orbits are described by changes in both radial and angular coordinate as electron orbits the nucleus. Now, if we do the integral PR dr, where PR is the radial momentum, we get a naught times h, and here integration of p phi d phi, where p phi is the angular momentum, gives you kh. K is the azimuthal quantum number and n is the principal quantum or radial quantum number here. As I mentioned, so PR is in the above expressions, PR is the radial momentum, p phi is the angular momentum and r is the radial coordinate. Phi is angular coordinate, nr is the radial quantum number and k is azimuthal quantum number, h is Planck's constant as usual. So, the relation between the principal and the azimuthal quantum number is given by principal quantum number n is your radial quantum number plus azimuthal quantum number. Then we discuss about Sommerfeld's relativistic correction. The electron's velocity varies at different points along the elliptical orbit, causing changes in its relativistic mass and thereby explaining fine details in atomic spectra. The relativistic mass is given by this expression. Here m naught is the mass of the electron when it is in rest, and v is the velocity of the electron and c is the velocity of light. So, this is the usual definition of relativistic mass of the electron. So, Sommerfeld showed that at aphelion or farthest from the nucleus, the electron's velocity is minimum, and at perihelion or closest to the nucleus it is maximum. This variation in velocity causes relativistic effects in the electron's mass and helps explain hydrogen's fine line spectra. So, you can see that as the velocity changes here, okay, so the relativistic mass of electron is changing with position, okay, and that is why it helps explain the hydrogen's fine line spectra here. So, this is the aphelion position, okay, so this is your farthest from the nucleus, and this is your focus, and this is your perihelion region, closest to the focus. So, when it is closest to the focus and when it is aphelion point or when it is farthest from the nucleus, you get two different relativistic mass of the electron, and this helps us to explain the hydrogen's fine line spectra. So, next we consider Sommerfeld's modified energy equation. So, Sommerfeld's relativistic corrections account for variation in electron velocity on elliptical orbit. So, the modified Sommerfeld's energy equation is given by this. So, this was the expression we had before, and then this was introduced later. So, So eccentricity and its coordinate condition. Eccentricity is the deviation of the elliptical shape of orbit from circularity and is denoted by epsilon. The relationship between the eccentricity and the azimuthal quantum number is this. So for an ellipse, it can be written as like this, and by comparing the two equations, we get k by n is nothing but b by a, means length of minor axis by length of major axis. The eccentricity of an elliptical orbit is the ratio of lengths of minor axis and major axis. Any variation in their values changes the eccentricity of the elliptical orbit. What is the necessary condition? The first case is when k is n. So when both major and minor axes are the same, or b equals to a, it implies that the length of both the major and minor axes are equal, then the orbit must be circular, right? Like here, you can condition is n equals to 4 and k equals to 4, you get circular orbit. Okay, now we consider n equals to 4 and k equals to 3. So when k is less than n, then b is less than a. So the minor axis of an ellipse is always shorter than the major axis, and as the value of k decreases, the eccentricity of the orbit increases. You can see that this is for n equals to 4 and k equals to 3. Next is n equals to 4 and k equals to 2. This is n equals to 4 and k equals to 1. So you see the eccentricity increases, okay, as k decreases. Now we talk about Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle states that there is a limit in the precision to which the position and momentum of particle may be determined simultaneously. So the position and momentum of a particle cannot be determined exactly at an instant. So this is the mathematical expression or mathematical formation of formalism of Heisenberg's uncertainty principle. He says that delta x times delta p is greater than or equals to h by 4 pi. So if you substitute delta p by m delta p, change uncertainty in momentum by uncertainty in velocity times mass, we get this expression. We arrive at this. Next comes Pauli's exclusion principle. So Pauli's exclusion principle is a special case of Pauli's principle, which states that if two identical fermions exchange their levels, the total wave function changes sign, and if the wave function is antisymmetric. And if two identical bosons exchange their levels, the total wave function retains its sign, or the wave function is symmetric. So Pauli's exclusion principle states that no two electrons in an orbital can have same 4 quantum number, means n, l, ml and ms. That means any orbital can accommodate maximum 2 electrons. Then we discuss wave mechanics from Davison-Gardner electron diffraction experiment and Einstein photoelectric experiment. It can be concluded that the classical concept of particle and wave meld together. Particle can behave like wave and wave can behave like particle. In 1924, a French physicist, Broglie, suggested that any particle, not only photon, traveling with a linear momentum p should have a wavelength given by de Broglie equation. Lambda is h by p, where lambda is the de Broglie wavelength, h is Planck's constant and p is the momentum of the particle. Thus, a particle with high momentum has a very short wavelength. So when in the denominator p is in the denominator, when the value of p is high, so lambda is very small, or we get very short wavelength. So this is the derivation of de Broglie's equation. So from Planck's quantum theory of energy, we know E is h nu, or if we substitute nu by lambda, we get hc by lambda, and from Einstein's theory of relativity, we get E is mc square. So equating if we equate these two expressions, we arrive at this lambda is h by mc. So if this equation 10 is also applicable for subatomic particles. For other particles, the equation will become lambda is h by m v. Here c is replaced, c is the velocity of light, c comes from this Einstein's theory of relativity. So for any particle, we can replace c, the velocity of light, by velocity of that particle, and m is the mass of that particle. Okay, next we discussed wave function psi. So, what is the significance of wave function psi? In quantum mechanics, the wave nature of particles is described by wave function psi that describes all dynamical information about the system. Psi can be positive, negative or complex, but the square modulus, this psi square psi, if psi is complex at any point, is proportional to the probability of finding the particle at that point. If the wave function of a particle has the value psi at any point x, the probability of finding the particle between x and x plus dx is proportional to psi squared dx. In 3-dimensional, the probability is proportional to psi square d tau, where d tau is dx, dy and dz. So, psi square is the probability density as we mentioned, and psi is itself sometimes called probability amplitude. Both negative and positive regions of a wave function may correspond to a high probability of finding a particle in a region. However, the presence of negative and positive regions of a wave function gives rise to the possibility of constructive and destructive interference between different wave functions. So, then we discuss Schrödinger's wave equation. So, wave particle duality of matter says that rather than travelling in a path, a particle is distributed in space. The mathematical representation of wave in quantum mechanics is called wave function psi that we already introduced. In 1926, an Australian physicist Erwin Schrödinger proposed an equation for finding the wave function of any system. So, the time dependent Schrödinger's equation can be written like this. This is time independent. Time independent Schrödinger equation is like this, where V is the potential energy, E is the called energy value, energy value, and then m is the mass, and this is for 3-dimensional. We get d2x by dx square, d2 by dy square, and d2 by dz square. And sum of these two we call delta, sum of these three we call delta square. So, you get minus h square by h cut square. H cut is your h by 2 by twice phi. H cross or h cut is h by 2 pi. And we can express this equation 12 like h cross square by 2m times delta square plus v psi equals to e psi, where h cross is h by 2 pi and delta square is d2 by dx2, d2 by dy2 plus d2 by dz2. In systems with spherical symmetry, three equivalent forms are: so psi square will be 1 by r d2 by dr square by 1 by r square, and then lambda square, and we can further simplify this one like 1 by r square del by del r square del by del r. So, we get, and then we arrived at this expression, where lambda square is 1 by sin square theta del 2 by del phi 2 plus 1 by sin theta del by del phi and sin theta del by del phi. In general case, the Schrödinger equation can, this is the general expression. So, H psi is E psi, where H is the Hamiltonian operator for the system. So, Hamiltonian operator is term consists of kinetic energy term as well as the potential energy term, and psi is the wave function. So, as I mentioned, this term is the kinetic energy term, and this term is the potential energy term. Or we can say this is kinetic energy operator here, since H is an operator and this is your V is potential energy operator. Now, the derivation of Schrödinger wave equation. So, Schrödinger wave equation can be derived from the classical wave equation. To understand that concept, let us assume a wave function moving along x axis with the velocity v. So, this is the particle, like it goes like this, okay, in the x direction, and this is the value of lambda or wave function. The amplitude of the wave at any time t is dependent on displacement, and the equation of wave of motion can be written as like this. So, if we at any instant, suppose the particle is here, the amplitude is 0, and if it is here, the amplitude is maximum. Okay, so, it depends on the value of x, and the equation of motion can be written like this. So, y is a function of both position x and time t. So, we can write y is function of x and f prime t, where fx and f prime t are the functions of coordinate x and time t. The nature of fx can be understood by standing wave. A standing wave is created in a string fixed between 2 points with a wave traveling between 2 points. When it strikes the other end, it gets reflected with the same velocity but with a negative amplitude, like this. Okay, this is so. This is there is a string fixed between 2 points with. So if you pull it down like this, then leave it, it goes like this. So the mathematical description of such wave motion is f prime t is a sine twice pi nu t, where a is the constant that depicts the maximum amplitude and nu is the frequency of vibration. Now putting the value of f prime t in equation 20 is here. If we substitute it, the value of f prime t here, we get y is fx a sine twice pi nu t. Now if we differentiate this equation with respect to time t twice, so we get this expression. This is equation 24. Okay, so from there actually we can further modify, and then we get if we differentiate this expression 22 twice with respect to x, we get this expression. So if we now use the value of equation 23 and 25 into equation 19. Here is the equation 19 here. Okay, so if we do these things, we arrived at this expression del 2f x by del x square is minus 4 pi square nu square y v square fx. So in equation 27, this is our equation 27. So the equation 27 becomes time independent. See, there is no time factor here. Since c is v times lambda, the velocity of the wave can be replaced by this expression. So equation 27, this will become this. So if we rearrange this one, we get equation 29. So del 2f by del x square plus 4 pi square by lambda square fx gives 0. So the fx now will be replaced by psi or simply psi x or simply psi. Then equation 29 will become del 2 psi by del x2 plus 4 pi square lambda square by lambda square times nu. Lambda square times psi gives 0. Now from de Broglie's equation we get lambda is h by mv. So equation 30 we get like del 2 psi by del x square plus 4 pi square m square v square by h square times psi gives 0. So further, total energy is sum of kinetic energy and potential energy. So E is mv square by half mv square plus v. So mv square we get 2 times E minus v. So if we substitute this here, we get del 2 psi by del x2 plus 8 pi square m by h square E minus v times psi gives 0. For 3-dimensional space, equation 34 here can be written like this. So this is for 1-dimensional. If we have 3-dimensional, we write like this. And then this is nothing but delta del 2x by del x square del 2 by del y2 plus del 2 by del z square gives delta square, and then we get the equation of Schrödinger equation. Then we discussed about mole concept. Okay, so the relative amount of a substance is known as the concentration, and it can be expressed in several ways. Like molarity, we know. So what is the molarity? The molarity of a solution is the number of mass of solute present in 1 liter or 100 ml or 10 to the 3 centimeter to the minus 3 of solution. The symbol of molarity is m. The unit of molarity is moles per liter or mole per decimeter cube. The mathematical formalism is if W gram of solute is present in V liter of solution and the molecular weight of the solute is m, then the molarity of the solution is W by m by V. So we get W by m times V. So what is the advantage and disadvantage of molarity? Aqueous solution of known molarity can be easily prepared by weighing the solute and measuring the volume of the solution. Although weight of a solute is not dependent on temperature, but volume of solution depends on it. So molarity depends on temperature. Molality. The molality of a solution is the number of moles of solute in 1000 gram of solvent. The symbol of molarity is lowercase letter m. Molality is expressed by mole per kg. So here the number of moles of solute in 1000 gram of solvent, and in case of molarity this 1 liter of solution. That's the difference. So here both are in mass, okay, solute as well as the solution or solvent. Okay. So, suppose the weights of the solution and the solute in the solution are W1 gram and W2 gram. So, the weight of the solvent is W1 minus W2 gram. Hence, W2 gram or W2 by m is the number of moles. M is the molar mass of the solute. The solute is dissolved in W1 minus W2 gram of solvent. Therefore, the number of moles of solute is dissolved in 1000 gram of solvent is W2 times 1000 by W1 minus W2 times m, or molality of the solution. So, what is the disadvantage and advantage of molality? Molality is useful to calculate boiling and freezing point. Moreover, it is not dependent on temperature, as weight of both solute and solvent is temperature independent. But weighing liquid solvent is difficult, which makes molality inconvenient for laboratory purpose. Then comes mole fraction. The mole fraction of a component is the number of moles that component divided by the total number of moles of all the components of the solution or mixture. Mathematical formalism: suppose for two component system, N1 and N2 are the number of moles of component 1 and component 2 respectively. So, the mole fraction of component 1 X1 is N1 by N1 plus N2. We have only two components. So, N1 is the number of moles of component 1 and N2 is the number of moles of component 2. So, in the denominator you have the total number of moles present in the mixture, and in the numerator you have the number of moles present for component 1. Similarly, mole fraction of component 2 is X2 is N2 by N1 plus N2, and total mole fraction X1 plus X2 is always gives you 1. So, if you have more than two component in your mixture, the sum of the mole fraction is always unity, as I mentioned. So, for a system with I number of components, suppose we have I number of components, so we just add them up, X1 plus X2 plus X3 like this up to Xi, it gives you 1. So, what are the advantages and disadvantages of mole fraction? Mole fraction is useful for connecting relative numbers of solute and solvents, and mole fraction is temperature independent. That is very good thing. So, in the next class we will discuss some problems and the solutions.